Good morning, everyone. I'm Rahul Chowdhury, and welcome to our comprehensive course on socket programming. Over the next session, we'll dive deep into the fundamentals of network programming, from basic socket management all the way to advanced asynchronous I/O patterns. Today, we're starting with the foundation socket management fundamentals. Let's begin with our main topic, socket management fundamentals. This is the cornerstone of all network programming, and understanding it well will make everything else we cover much clearer. First, let's answer the fundamental question: what exactly is socket management? Think of sockets as endpoints for communication between processes, whether they're on the same machine or across the internet. Socket management involves creating, configuring, monitoring, and properly closing these communication channels. It's absolutely critical because poor socket management leads to resource leaks, connection failures, and scalability issues. Next, we need to understand the communication layers that make socket programming possible. The network stack is like a layered cake. We have the physical layer at the bottom, then data link, network, transport, and finally the application layer where our socket code operates. Each layer has specific responsibilities, and sockets primarily work at the transport layer with TCP and UDP protocols. Finally, let's acknowledge the programming challenges we'll face. Socket programming isn't just about making connections. We need to handle timeouts, manage buffer sizes, deal with partial reads and writes, handle connection drops gracefully, and ensure thread safety in concurrent applications. These challenges are exactly why we need systematic approaches to socket management. As this summary perfectly captures, socket management truly forms the foundation of all network programming. Whether you're building web servers, database clients, or distributed systems, the principles we'll cover today will be your building blocks. In our next section, we'll dive deeper into network fundamentals to build on this foundation. Now that we've covered the socket management fundamentals, let's dive into the network fundamentals that form the foundation of all socket programming. These concepts are essential for understanding how data flows across networks. First, let's examine the two primary transport protocols, TCP and UDP. TCP provides reliable, connection-oriented communication with built-in error checking and data ordering. UDP, on the other hand, offers fast, connectionless communication without guarantees, perfect for real-time applications where speed trumps reliability. Next, we have IP addresses and ports, the addressing system of the Internet. Think of an IP address as a street address for a computer, while the port number is like an apartment number. Together, they create a unique endpoint that your socket can connect to or listen on. The client-server architecture is the backbone of most network applications. The server listens for incoming connections on a specific port, while clients initiate connections to request services. This asymmetric relationship defines how most socket programming works. Finally, understanding the network stack layers helps you see the big picture. From the physical layer handling electrical signals, up through the transport layer where TCP and UDP operate, to the application layer where your socket code lives. Each layer has specific responsibilities that enable network communication. These networking fundamentals provide the conceptual framework for everything we'll build with sockets. In our next section, we'll explore how sockets, connections, and kernel queues work together to implement these networking concepts in practice. Perfect. Now that we understand the fundamental networking concepts, let's dive deep into how sockets, connections, and kernel queues work together at the system level. First, let's examine the socket creation and binding process. When your application creates a socket, the kernel allocates a socket structure and assigns it a file descriptor. The binding process then associates this socket with a specific network address and port. Next comes connection establishment through the famous three-way handshake. This is where the client sends a SYN packet, the server responds with SYN-ACK, and finally the client acknowledges with ACK. This process creates a reliable, ordered connection between two endpoints. At the kernel level, each socket maintains separate send and receive queues. These queues buffer incoming and outgoing data, allowing your application to read and write data asynchronously while the kernel handles the actual network transmission. Understanding socket states is crucial for debugging network applications. Sockets transition through various states like listen, SYN sent, established, close wait, and time wait, each representing a different phase in the connection lifecycle. Finally, the listen backlog and accept queue mechanics determine how many pending connections a server can handle. The backlog parameter in your listen call controls this queue size, which is critical for handling high-traffic scenarios without dropping connections. These kernel-level mechanisms work together seamlessly to provide the socket abstraction we use in our applications. In our next section, we'll put this theory into practice with a socket connection simulation. Now that we understand how data flows through kernel queues, let's dive into the actual mechanics of sending and receiving data through sockets. This section covers the fundamental operations for socket data transmission and the critical best practices you need to handle real-world networking scenarios. The two core system calls you'll work with are send, for transmitting data to a socket, and recv, for receiving data from a socket. These are your primary interfaces for socket communication. Here's a crucial concept that trips up many developers: partial operations. The send function may not transmit all your data in one call, and recv may receive less data than you requested. You must always check return values and handle incomplete operations. Understanding blocking versus non-blocking behavior is essential. Blocking operations wait for completion, which can freeze your program. Non-blocking operations return immediately, allowing your program to continue processing other tasks. Finally, robust error handling is critical. Always check ERNO for specific error details and learn to handle common cases like EAGAIN and EWOULDBLOCK, which indicate you should retry the operation later. These concepts form the foundation of reliable socket programming. In the next section, we'll test your understanding with a comprehensive quiz before moving into advanced programming patterns. Perfect, building on the kernel concepts we just covered. Let's now explore the essential design patterns that make socket applications robust and scalable in production environments. Socket programming patterns are proven architectural approaches that solve common challenges in network application design. These patterns help us handle concurrency, manage resources efficiently, and build systems that can scale under load. First, let's examine the single-threaded event loop pattern. This approach uses non-blocking I/O and event-driven programming to handle multiple connections on a single thread. It's incredibly efficient for I/O-bound applications and forms the foundation of systems like Node.js and Nginx. The thread-per-connection model takes a different approach, spawning a new thread for each client connection. While this provides isolation and simplicity, it can quickly become resource-intensive as connection counts grow. To address scalability concerns, we use the thread pool pattern. This maintains a fixed number of worker threads that process connections from a shared queue, providing the benefits of multi-threading while controlling resource usage. Producer-consumer patterns are essential when socket applications need to process data at different rates. Producers generate data from network connections while consumers process it asynchronously, often using queues or buffers to manage the flow. Finally, connection pooling is crucial for applications that make frequent outbound connections. Rather than creating and destroying connections repeatedly, we maintain a pool of reusable connections, dramatically improving performance and reducing overhead. These patterns aren't mutually exclusive real-world applications, often combine multiple approaches. Next, we'll dive deep into asynchronous I/O techniques that make these patterns even more powerful. Building on those socket programming patterns we just explored, let's now tackle one of the most powerful techniques in network programming, asynchronous I/O. This is where we really see the difference between basic socket handling and high-performance network applications. First, let's understand the system calls that make async I/O possible. We have three main approaches here: select, poll, and epal. Each represents an evolution in how we can monitor multiple file descriptors efficiently. Select is the oldest but most portable. It works across all Unix-like systems. Pol improves on Select's limitations with file descriptor numbers, and Epal is Linux's high-performance solution that can handle thousands of connections with minimal overhead. This event-driven programming model is what powers modern web servers. Now, when it comes to programming patterns, we have two dominant approaches in the async world. The callback-based model was the original way. You register functions to be called when events occur. But this can lead to what we call callback hell with deeply nested code. Promise-based async programming emerged to solve this complexity. Promises provide a cleaner way to handle asynchronous operations, making code more readable and maintainable. Languages like JavaScript and Python have embraced this pattern extensively. The performance benefits are dramatic. While synchronous I/O blocks a thread for each connection, async I/O can handle thousands of connections with just one or a few threads. Modern frameworks like Node.js, Python's Asyncio, and Go's Goroutines all leverage these principles. The key benefits speak for themselves, handling thousands of simultaneous connections with efficient resource usage and minimal memory footprint per connection. This is exactly what we need for building scalable network applications. Next, we'll see these concepts in action with a practical demonstration. Perfect. Now that we understand the theoretical foundations of asynchronous I/O, let's put everything together with a comprehensive socket management demonstration. This is where we'll see real code in action. We'll start with a complete client-server example walkthrough. This isn't just theory anymore. You'll see exactly how to establish connections, manage socket lifecycles, and handle data flow between client and server components. Next, we'll dive deep into error handling implementation. This is crucial for production systems. We'll cover connection timeouts, network failures, and graceful degradation strategies that we discussed in our socket fundamentals. Then we'll explore performance monitoring and debugging techniques. You'll learn how to instrument your socket code, identify bottlenecks, and use the debugging tools that complement the kernel queue concepts we covered earlier. We'll also examine common mistakes and prevention tips. I'll show you the pitfalls I've encountered over 15 years of network programming, things like improper buffer management, blocking operations, and resource leaks that can crash your applications. Finally, we'll wrap up with production-ready socket management practices. This brings together everything from our socket programming patterns and asynchronous I/O discussions into a cohesive, scalable approach you can use in real-world applications. This demonstration will solidify all the concepts we've built up throughout this course. You'll see how the fundamentals, connection simulation, data handling, and programming patterns all work together in practice.